Hi, everyone, and welcome to a new topic. Actually, the topic that we are going to be covering today is part of a big chapter on probability. But we're not going to focus a lot on probability itself. We'll be focusing more on what's called counting techniques. How do you count things? And we will be specifically talking about permutations and combinations. So in this lecture, the focus will be on permutations, and the next one will be on combinations. So you will learn, after we finish this discussion, you will learn how to solve problems using what's known by the fundamental counting principle. The word principle in mathematics means it's an undiscussed or a non-negotiated mathematical result. So if you kind of like a given mathematical result, we call the principle of mathematics or a mathematical principle. And we'll be solving problems involving permutations. And when we say permutations, let's say when you have n objects, and then in how many ways you can arrange those objects. If some of the objects are duplicated, then we'll be learning how to do permutations of duplicated or items from which we have some of which are duplicated. Here is what's called the counting principle or the fundamental counting principle. Suppose that you have an experiment, and this experiment has m distinct ways. And followed by this experiment, you have a second experiment, and the second experiments can be done in n distinct ways. In how many ways you can do how many ways you can do the experiments, both experiments back to back? Well, you have m times n distinct ways in which you can do these two experiments one after the other. This might sound a little bit confusing. Let me give you an example, a very easy example. Suppose the first experiment or the first task, you can call task if you want to. Let's see, for example, you want to choose, let's say you have 7 cars. Let's say you have 7 cars. And you would like to, the first experiment is to, or the first task is to drive your car and then to go to a shopping mall, let's say, and then we have, let's say 10 shopping malls. So this is the number of cars. And then this is, let's say, malls, shopping malls. So in how many ways you can do this? Well, you have 7 cars, right? You can take the first car, the second car, and the third car, and so we cannot drive more than 1 car, right? So this is your m right here. So you have m different ways to do the first experiment or the first task. And once you get into the car, then you need to decide which mall you are going to go to. We are going to assume that you're going to go to 1 mall and not 2 or more malls, just 1 mall. And then you have 10 choices. So this is your n. So in how many ways you can do the whole thing? Well, you have 7 times 10, we have 70 different ways. For example, you can take the blue car and go to the Millennium Mall, let's say, or you can take the blue car and go to the Fashion Square Mall, or you can take, I don't know, the white car and go to Fashion Square Mall, or the white car go to Altamont Springs Mall, and so forth. So this is just a very basic example to show you how it goes. So if the first experiment can be done in m distinct ways, and the second experiment can be done in n distinct ways, then in how many ways you can do both experiments back to back? Well, you have m times n, and this is the example I gave you just to illustrate how it goes. And this is known by the fundamental principle of counting, and it's a very strong mathematical principle that will help us to solve a lot of more complicated examples. You will see how are we going to use this principle to actually deal with trickier situations. Well, here is one of those situations. Suppose we are going to count how many passwords to create. So it says here in this exercise, a password used to gain access to a computer account is to consist of 2 lowercase letters followed by 4 digits. Right, so we have 2 lowercase digits followed by 4 digits. The first digit, the second one, the third one, and the fourth one, right? So these are the letters, and those are the digits. Determine how many different passwords are possible if repetition of letters and digits is permitted. For example, you may have your password to be AA 0000. That could be a password, right? Because the exercise says here, repetition is permitted. In how many ways you can do this? What is the total different number of passwords you can create? Well, a lot, really. Well, how does the fundamental principle counting help here? Well, to choose the first letter, right? So let me draw this again. The first letter, the second letter, and the 4 digits. 1, 2, 3, 4. So to choose the first letter, well, how many possible cases or how many ways you can do this? Well, you have 26 choices. You can decide the first letter to be A or B or C or D all the way till Z. So you have 26 choices. Now, how many choices you have when you are about to decide the second letter? Well, since here repetition is permitted, right? I have also 26 possibilities. Now, how many choices you have for the first digit? Well, I have 10 possibilities, 0, 1, 2, 3, 4, all the way till 9. So I have 10 choices. Can I, for example, if I, let's say, choose 5 here, can I choose 5 here? Yes, you can, but it doesn't have to be 5 here. It could be anything really, but you still have 10 choices here, 10 choices, 10 choices. So in how many ways you can do the whole password? Well, because of the fundamental principle of counting, is going to be 26 times 26 times 10 times 10 times 10 times 10. And this is the number of how many passwords that you are going to get. So the solution will be, like I just said, would be 26 times 26 times 10 to the power 4, 10 times 10 times 10, 4 times, which is 6,760,000 passwords. And of course, you ended up picking just one password. You're not going to choose those passwords. So just to give you the idea that you have 6,760,000 choices. Okay, so let's do another exercise. Well, let's finish this exercise. What happens now if the repetition is not permitted? Means that you cannot pick the same digit, the same digit twice or the same letter twice. As you can see here, when I pick here, let's say A, I cannot pick A here. So the first letter I'm going to get, I have 26 choices. But the second one will get only 25. Why 25? Because I need to avoid picking the first letter. Well, the same thing here, the first digit to choose, I have 10 choices. Next one, I have 9 choices, 8 choices, and 7 choices. I think you get the point here. So if it is not permitted, so 26 is how many choices I have to pick the first letter. 25 is how many choices do I have to pick the second letter. Then 10 possibilities for the first digit, 9 possibilities the second digit, 8 for the third one, and 7 for the last digit. In total, I have 3,276,000 different passwords. As you can see, I have less choices than the previous one because repetition is not possible. So I was saying that we are going to have less numbers or a total of less passwords than the previous one because here now repetition is not permitted. Okay, well, we can keep working. Here's part C of the same exercise. Suppose the first letter must be a vowel. Well, means that I have only 5 choices. The first digit cannot be 0, means that the first digit means that I have only 9 choices to pick the first digit, and repetition of letters and digit is not permitted. Well, you get the point. So I have 5 choices. Then the next one, I will have 25 choices because I cannot pick the one of the letters before. right? So as you can see here, 5, because it has to be a vowel, either A, vowel, either A or E or I, O, U. 25, because the second one, you pick any letter you want except the one that you picked up front. So I have 26 minus 1. The first digit cannot be 0, so I have 9 choices. The second one can be 0, right? The second one can be 0, can be anything except what you picked for the first one. So we're back to 9 again. Then since we are not allowed to do repetition, it's going to be times 8 times 7. And this time we have 567,000 different passwords. Still a big number, but a lot less than the previous ones. Okay, what is a permutation? The word permutation in mathematics means if you have objects and then you shuffle those objects around and you put them in an order, then it's called a permutation of these objects. So as you can see on the slide, a permutation is any ordered, and the word ordered is very important. Every time you talk about permutation, the order matters. Is any ordered arrangements of that given set of objects. Well, here's a big theorem. It says the number of permutation of n distinct, this is another key word here, distinct. Suppose that you have n distinct items, is what's called n factorial. So if you have n distinct objects, you have n factorial ways to do permutations. And what is n factorial? It's n times n minus 1 times n minus 2 times all the way to the 1. For example, what's 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120, right? Because 1 times 2 is 2, 2 times 3 is 6, 6 times 4, 24, 24 times 5 is 120. And this is called 5 factorial. So here, let's suppose that I have 5 different objects, 5 different cars, right? In how many ways I can line them up? I have 120 different ways to do that. You will see in the previous examples how this works. Well, here is an example. In how many different ways can 7 different cars be arranged next to one another? Well, it's 7 factorial, right? Which is 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040 different ways. Suppose that you have 7 cars, right? And you want to pocket them next to each other. 1, 2, 3, 4, 5, 6, 7, right? In how many ways you can do this? For example, this is the blue car, this is the gray truck, this is the van, and this is the pickup, the yellow pickup truck, I don't know, whatever. You have 7 different cars, 7 different vehicles, let's say. In how many ways you can line them up? Well, you have 5,040 different ways. Right? So you can just rearrange these things another way, and there you have another way, and so forth. But again, different. You see, we have if I go back to this example, if lining up cars, well, cars are different, right? You have different cars. Suppose that you have, let's see, 2 of these cars are identical. Kind of, you just drove them out of the dealership, brand new, identical. You cannot even make a difference. So they don't have any license plate to make the difference between them. So now the problem becomes a little bit more trickier, right? So if you have 2 identical cars or 3 identical cars of this among those 7 cars that are exactly, they look the same. For example, if I close your eyes and I park one, you cannot tell which really one is it. So if you have identical items among the items that you are going to rearrange, then the problem becomes a little bit trickier. And we're going to do the solution of that. So n factorial, this formula n factorial will be used if you have n distinct cars, means none of the objects are the same. Well, here's another example. Consider the 5 letters A, B, C, D, E. In how many distinct ways can 3 letters be selected? So you need to select 3 letters from these 5 letters, right? And arrange them. For example, I can put A, C, E. That's one way to do it. Or I can put B, E, D, another way, and so forth. In how many ways you can do this? Well, here is where the principle of counting matters. And actually, this problem fits into what's called an NPR problem. But let's do this, let's do the solution without referring to anything. So I need to pick 3 letters from these 5 letters. How many choices you have to pick the first letter? Well, you have 5 choices. Now it's time to pick the second letter. How many choices you have? Well, now you have only 4 choices. And how many ways you have to pick the last one is 3 choices. So 5 times 3 times 4 is the number of ways you can. Remember, repetition is not allowed. That's why I put 4 here. If repetition was allowed, I would have put 5 and then 5 here again, right? But since I cannot pick the letter that I picked before, so the number will be decreasing. The number of choices will be less. So, and then you have the solution. As I told you before, this fits into a more, I mean, we can have this into a formula by itself. So let's do the solution. Like I told you, is 5 times 4 times 3, which is 60. Well, in general, we have this formula here. It may sound too difficult, but it's not really. So the number of permutations possible when R objects are selected from n distinct object, that's what you get. It's n factorial divided by n minus R factorial. So again, suppose that you have n objects, distinct objects. So none of the objects look the same, right? So that's why I'm putting different things on each object so they don't look the same, right? So you have n objects, like 17 objects, 100 objects, 4 objects. And then you are going to pick, you're going to choose R objects. You're gonna, for example, from these 17 objects, you need to pick 3 objects. Let's say I'm gonna pick, let me change the color here so I can tell you one. You're gonna pick, let's say 3 of them. I'm gonna pick this one, and this one, and put them here. Next time I'm gonna pick this one, and this one, then put them here. The order matters. In how many ways I can do this? Well, this is the formula. Take your number n, the large number, put the factorial of it. If it was 7, let's say, you put 7 times 6 times 5, 4, 3, 2, 1, right? Which is 5,040. And then n minus r. So suppose that n is 7 objects and r is 3 objects. I'm going to pick 3 objects. It's going to be 7 minus 3 factorial, which is 4 factorial. And what's 4 factorial? It's 4 times 3 times 2 times 1. And then you take 5,040 divided by this number, which is 24. So 5,040 divided by 24. So let me give you an exercise. Okay, here's an exercise that illustrates how to work with the NPR formula. You are among 9 people forming an astronomy club. Collectively, you decide to put each person's name in a hat to randomly select a president, vice president, and a secretary. In how many ways we can do that? In how many ways we are going to pick a president, vice president, and secretary? Well, again, is it a permutation problem? Yes, because the order matters. Because the first person we're going to pick is going to be the president. The second person we're going to randomly pick will be the vice president, and the third will be a secretary. So what is n? How many objects do you have? Well, you have 9. You have 9 objects. How many are you going to pick? Well, 3. So what's the formula? It's going to be 9 factorial divided by 9 minus 3 factorial, which is 9 factorial divided by 9 minus 3, which is 6 factorial. And what is 9 factorial? Is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, whatever that is. And what is 6 factorial? Is 6 times 5 times 4 times 3 times 2 times 1. Well, this is how you can do these things, you know, I would call it the hard way, right? But there are 2 different other ways to do it. So again, here is the solution: n equals to 9 and r equals to 3, and write it out, right? So this is your 9 factorial. And as you can see, we can use a little bit of algebra. We can cancel things out, right? So 6 divided by 6 is 1, 5 divided by 5. So those things will go away. And you end up with what? Just 9 times 8 times 7, which is 504. So we have 504 different ways to pick a president, vice president, and a secretary from a pool of people, from a pool of 9 people, which is a lot, really a lot, right? So I am going to post a video to show you how to use a calculator to compute this. If you have TI 84 or 83 or 84 plus or 83 plus, I'm gonna put a video to show you on Canvas to show you how can you bypass all this calculation and how can you compute NPR directly. Now we're going to go back to that difficult situation when you have n objects, but among those objects there are repeated or identical objects. So suppose again you have n objects and you have n1 of the objects are identical, n2 of the objects are identical, and so forth. This sounds a little bit too mathy. I'm going to give you an example later on, but this is the formula. This is the number of permutations you can this is the total number of permutation or number of arrangements of all these n objects. It's going to be n factorial divided by the product of the multiplications of n1 factorial, n2 factorial, all the way to nr factorial. Again, if you read this for the first time, it's too complicated, but if I give you an example, if you follow the example along, you should be just fine. Actually, it's not that bad at all. Okay, in how many different ways can the letters of the word Cincinnati be arranged? So how many objects do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my n is 10, right? But as you can see, C is repeated how many times? 1, 2. So n1 is 2. The I is repeated 1 time, 2 times, 3 times. So n2 is 3. The n is repeated what? 1, 2, 3, right? So we have 3 n's. So n3 equals also 3. So we already did the C, the I, and A is repeated only 1 time. So if it's only 1 time, don't bother to do that. T is only 1 time. So here, the solution will be 10 factorial divided by 2 factorial times 3 factorial times 3 factorial. Yeah, so here it is. So of the 10 letters, there are I's and there are 3 I's, right? There are 3 are I's and 3 are N's and 2 are C's, right? The number of possible arrangements are 10 factorial divided by 3 factorial times 3 factorial times 2 factorial, or 2 factorial times 3 factorial times 3 factorial. And you put this in a calculator, it gets you 50,400 different ways to rearrange the word Cincinnati. For example, you can put one of those 50,400 different ways is already in here. Or I can put C, C, I, N. Well, I have how many I's? 1, 2, 3 I's. I'm going to put the third one here. And A and T. Yeah. So that's another way among those 50,400, right? So of course, nobody will ask you to list them all because it's going to be ridiculously too long. Yeah, well, this is it. So what we learned is we learned the fundamental principle of counting, which is the principle that is used behind all these formulas we covered today. And particularly, we talked about arrangements or permutation of n distinct objects when the objects are all different from each other. And we learned the formula of how to make permutations of n objects, but some of these objects and objects are repeated or identical. And we come up with this new formula here, this one here, the one we just did before, this one right here. And of course, before we did this, we talked about the factorial of a number. What is the factorial of a number? It's this number times the number right below it times the number right below that, and so forth. For example, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, I hope this was not too bad. If not, please let me know if you have questions. But I encourage you to go and start your homework. And by the way, the homework, I think you should feel more comfortable about this topic.